Now we want to further this discussion and we want to understand Markovnikov rule and the limitations of Markovnikov. Now, what if I have an alkene like this? And we don't talk about modified Markovnikov, we just talked about Markovnikov rule. What if I HBr? Of course, I know that I'm adding hydrogen and bromine, right? Then according to Markovnikov rule, hydrogen will join to the carbon with more hydrogen. They'll give me the major product. And let's see which of this carbon has more hydrogen. Then you notice we have a problem, right? This carbon on the left-hand side, there's only one hydrogen and R group. This carbon on the right-hand side, there's one hydrogen and one R group. So you notice now we have a problem. If both of these carbon have the same number of hydrogen, then where would the hydrogen go to? You notice we have a bit of an issue here. Now, even if I consider modified Markovnikov rule, we have a similar limitation. Markovnikov is based on the idea that my alkene carbon must have a different number of hydrogen. Hydrogen joins to the carbon with more hydrogen. Electrophile joins to the carbon with more hydrogen for modified Markovnikov rule. And if my alkene carbons have the same number of hydrogen, then Markovnikov rule is like totally useless. It's a total breakdown. We cannot use Markovnikov rule anymore if my alkenes, both of my carbon, which is part of the alkene, we have the same number of hydrogen. So we want to be able to appreciate that. Now, if I cannot use Markovnikov rule, then the next thing is, can I try to talk about the stability of my carbocation ion, which is what we have talked about previously, right? No problem. I can at least try to draw the two carbocation ions that can be formed. Let me just consider which one is bonded to more R groups. So therefore, that guy will be more stable, and therefore it will be more likely formed, and so therefore it will be the major product. So let us try to consider that. Now, if, based on the same guy, I work out the first step, of course, hydrogen, it is the electrophile. Hydrogen joins to either carbon 2 or carbon 3. Now, if hydrogen joins to carbon number 2, the carbocation ion will be something like this. If hydrogen joins to carbon number 3, my carbocation ion will be something like this. So therefore, I have two different carbocation ions, and I want to compare the stability for these two guys. Now, which is the one that is more stable? Which one has more electron donating R groups? Now, if I look at the carbocation ion on the left-hand side, this carbon 3 is attached to one ethyl group and two ethyl groups, two electron donating groups. Okay, this other carbocation ion is attached to one methyl group and one propyl group, also two electron donating groups. So now you notice we have a problem, right? If both of them are attached to two electron donating groups, so which one of them is more stable? Because what we learn is more electron donating group, carbocation ion more stable and more likely form. Eventually, you'll give me the major product. But if both of them have the same number of electron donating R groups, then I don't know which one is more stable. Okay, we still have one more concept that can help to save this situation, because you notice even if this is two groups versus two groups, but the size of the group is different, right? This is two of them are ethyl group, two carbon and two carbon. This one is one propyl group and one carbon group, one 3-carbon group and one carbon group. So if it is one R group versus one R group, is there a difference in electron donating effect? The answer is yes. The bigger the R group, the more donating it will be. So one carbon group is less donating than two carbon group. Two carbon group is less donating than 3-carbon group. The more carbons we have, the more electrons to donate. So we still can try to take that into consideration and we see which one is more stable. But you notice if I have two ethyl groups, 2 carbon plus 2 carbon versus propyl plus methyl, 3 plus 1, then now the problem will be the same. I can't tell which one is overall more stable because I know that a 3-carbon group will be more donating than a 2-carbon group. So if it is this group versus this group, this 3-carbon group is more donating. But if I compare this methyl group versus this ethyl group, this ethyl group is more donating than this methyl group. So you notice it's actually very, very difficult if I have a more donating group with a less donating group versus two okay donating groups. So how do I know overall which one is better, which one is worse? You notice it's actually very, very difficult for us to determine which one is more stable. Now, the conclusion to this, because we want to leave it open-ended, we still need one more idea before we can try to reconcile this concept. But up to now, that is what we want to be able to appreciate is the limitation of Markovnikov rule. Because for Markovnikov and modified Markovnikov, the criteria is my alkene carbon must have a different number of hydrogen. Then the hydrogen will join to the carbon with more hydrogen, or the electrophile will join to the carbon with more hydrogen. And if the alkene carbon has the same number of hydrogen, then you notice my Markovnikov becomes not particularly useful. So we want to understand the limitations of Markovnikov rule. Again, if you understand the limitation of it, then we can appreciate Markovnikov rule a lot better, correct? So we will keep this idea in mind, and eventually we will come back to this and we will address this, but we still need to go through a few more function groups first before we can handle this. But having said that, for this particular exercise, if we can't really tell which one is more stable, which means that the difference in the stability is very, very small. And so therefore, if you do addition reaction involving these two guys, the proportion of these two products will be very similar. That means the difference in the proportion of the major minor product will be very close. Maybe the major product will be like 50-something%, the minor product is 40-something%. The percentage is very close. I don't think it will be 50%, 50%, because it will mean that the stability for these two guys are exactly the same. If one guy is like slightly more stable than the other guy, but we can't tell which is more stable, then the one which is slightly more stable will be 50-something%. The other one will be something 40-something%. The bigger the difference in the stability of my carbocation, then the difference in the major minor product will be bigger. Maybe like 70-30%, 80-20%, or maybe like 90-10, 90%, 10%. If the difference in stability is very, very different, then the proportion of the major minor product, the difference will be also very big. But if the stability for these two guys, we cannot really tell, so which more or less means that they're roughly the same. So we would expect the percentages of these two guys to be also roughly the same. But again, we still cannot tell who is more stable. Okay, based on all the concepts that we have learned, we have already exhausted all possibilities. We don't have any capacity to try to predict which one is more stable. So that's a limitation, which I think is good to appreciate.